In this module, we introduce file systems. In our lecture on disk geometry, we describe how disks are laid out as platters, multiple platters in a hard drive, where each platter has a head that reads data that's laid out on the hard drive. Hard drives are laid out with concentric circles called tracks. Here we see a track on the outer edge of a hard drive platter. Sectors are pie-shaped wedges within a track. It's the unit of allocation that the hard drive's head uses to put data onto the platter. And typically operating systems will group sectors into what are called clusters. So for instance, this sector, this sector, this sector, and this sector, these four sectors might be grouped by the operating system into a cluster. And the operating system will use the cluster as its basic unit of allocation. Some other terminology. Low-level formatting is done by the manufacturer, where they lay out the cylinders, tracks, sectors of a disk platter. Partitioning is done by either the operating system or computer manufacturer who is making the computer, or by a user. The idea is that partitioning breaks a single hard drive into a number of logical hard drives. For instance, a single drive might have a C, D, and E partition in Windows. High-level formatting, the kind that users do to disks, is the idea of looking for bad sectors and putting a file system, the topic of today's talk, onto the partition. Note that I said that file systems are put on partitions. If the hard drive has only a single partition, then that single hard drive, all of its space is controlled by a single file system. However, if a single hard drive is partitioned into, say, C, D, and E, each partition, C, D, and E, can have its own and possibly different file system. So what is a file system? A file system is used by the operating system, an operating system like Windows, for instance, to manage the storage of the files on the permanent storage media of the computer. So for instance, if a computer has a hard drive with 3 partitions, files can be laid out on those partitions by Windows. Where it lays them out, exactly what sectors and clusters it puts the contents of the file into on the drive, is managed and kept track of by the file system. Current Windows operating systems like Vista and XP use the NTFS file system to keep track of where files are on the storage media. The file system also keeps metadata about the files that they manage. For instance, it keeps track of the creation, access, and modified time of each file. It keeps track of the privileges. Can anyone read the file, or can anyone or just specific users write to the file? Let's take a look at a relatively simple file system. The file system that uses a file allocation table, or FAT, is one of the original file systems. FAT12 and FAT16 were used on floppy disks by the early Windows and DOS operating systems. FAT32 was used by early Windows systems and is still in use today as a file system on flash drives. Let's take a look at how the FAT file systems generally work. Generally, the FAT file system will keep a data structure on the disk called the root directory. The root directory is a listing of file names and the metadata about the files, for instance, the creation time, the access time, some file attributes like whether they're read-only or not. So the root directory is laid out usually in a specified place on the partition or in the file system that keeps track of information about the files that are in the partition. FAT also uses the FAT itself, the file allocation table. So we see 2 data structures. One is the root directory, which is really, think of it like a listing of the files and their attributes. And the file allocation table keeps track of where files are laid out on the disk, what clusters are being used. If a file requires more than one cluster, which is often the case for large files, then the file allocation table keeps a chain of pointers indicating what clusters the file occupies. So let's look at the example. Here we have in the root directory someone saved a file called test.dat. Now there would be some information about the file that's not shown here, but typically there would be creation date and time, and whether it's read-only and who owns it. All that stuff would be here in the root directory. But here we see an indication of the first cluster. Where does the first part of the file reside? And it's saying it's residing in cluster 4. So that if the user wanted to open this file, the operating system could instruct the head of the spinning platter to go find cluster 4 and start to read the contents of test.dat. Now, assuming test.dat requires more than one cluster, the operating system would then go to the file allocation table, this, and say, after I finish with cluster 4, which the root directory said was my first cluster, where do I go to read the next bit of the file? And it says to go to cluster 7. So note here that files are not necessarily contiguously laid out on the platter. In this case, the first cluster of the file was in cluster 4, but then the second cluster of the file jumped to cluster 7. This is done so that the operating system can manage the space on the disk more efficiently by breaking files up and tucking in parts of it wherever it can. So again, if the entire test.dat had to be read, say for instance into an editor of some kind, the head would go to cluster 4 first because the root directory tells it to do that. Then it would start to follow what the FAT tells it to do. It tells it to go to cluster 7 next and read all of that. In cluster 7, we see that we then have to go to cluster 6 for our next reading of clusters. Cluster 6 says, go read the next part in cluster 10. And up at cluster 10, we see FFF, which is an indication for the end of file, telling the operating system that you've read the entire file in now, you don't need to read any more. So this is how a file allocation table lays out and places and then keeps track of the data that it's put on the platter. Here we see a hex editor view of a file allocation table. A hex editor is a tool that allows the user to look at the values stored in clusters in hexadecimal. It takes some getting used to, but people who are very good at operating systems and forensics often find it very useful to become good at being able to use a hex editor to really look at the low-level data that's stored on a disk. So here the hex editor is showing that the first FAT entry is in 188028, and it's pointing to 188029. So here we see 188028 location, and in it it's saying go to the next cluster, which is 188029. That is the hex equivalent of what we saw in our previous slide, where we saw that cluster 4 started it, but cluster 4 pointed to cluster 7. So we see the idea of a file allocation table having some location on the disk and then pointing to where the next location is. This particular hex editor shows all the clusters of the same file in a color. So here we see in red all of the clusters of a file, and we can follow them from 188029 to 188030 to 31 to 32 to 33. We can see that this operating system, and most do this, when possible, lays the file out in contiguous locations because it's faster for the head to retrieve and access files in contiguous locations. But due to the allocating and deallocating of space on the platter by the operating system, it doesn't have to be contiguous. Here, for instance, we see that in location 188038, which is this location where my cursor is moving, it's saying that the next cluster is in 188045, meaning that there's some other stuff in these other clusters. So it skips down to here and then follows up. And finally we see in red the end of file marker, which on our previous slide was the FFF, indicating that the head no longer has to search out. We've read in all of the file. So this slide is pictorially showing how a root directory points to a file allocation table, and the file allocation table has a chain of pointers. This is the actual view that a forensic examiner would have using a hex editor to look at the values on a disk. Here's a list of some of the information that the root directory will keep, the metadata it will keep about files. In FAT12 and FAT16, the name, the 3-character extension, the size of the file, some date information, its starting cluster, whether it's hidden, whether it's a directory, whether it's read-only. Some of this information is kept or all of this information is kept in the root directory. FAT32 added some other things like the creation time, the checksum of the file, the creation date, whether it's a linked file or not. So file systems keep various information, and TFS adds even more information about the file that it keeps. A user, in particular a forensic examiner, can read the file allocation table in the root directory using tools. We saw previously a hex editor used to follow the file allocation table, or the FAT. Here we're using a program called Runtime Software's Disk Explorer for FAT, which will find and open up and give a nice view of the root directory. So here we see the root directory. So we see on a file called reading assign, its status, its checksum, and some information about it. Also note, and we'll talk about this in a moment, but while we're here, let's take a look. The special character here indicates that this file has been deleted. So deleted files do remain, at least for a while, in the root directory and have a special character that leads them to indicate they've been deleted. Since deleting files is very important in forensic, it's a great source of evidence, let's understand how files are deleted. In a FAT32 file system, and in DOS file systems, deletion is done by putting a special character, a hex E5 or in decimal 229, that in some of the text editors looks like this character, as the first character of the file name. So basically it renames the file in the root directory with a special character leading it. When the file is deleted, it gets this special character, plus the file system goes into the FAT and basically puts 0 pointers into all of the cluster containers in the FAT, saying that those clusters are now unallocated, which means they're available for the operating system to allocate to a new file. This is a key point. When files are deleted, they're not wiped off the disk innately, at least in the FAT32 file systems. Instead, they're marked as deleted with a special character, and the clusters that they occupied are marked as unallocated in the FAT. But until the operating system reallocates those clusters and it writes something else there, the data that was in that file is still there and can be retrieved with forensic tools, or sometimes with forensic tools plus techniques such as data carving. We will now do an example of using the FAT file system to save and delete files. Here we see the original configuration that we described previously, where in the root directory there's a single file called test.dat. Its first cluster is cluster 4. From cluster 4, the second cluster was in 7. From 7 we went to 6, from 6 to 10, and the final cluster of test.dat was in 10, as indicated by the end of file marker here. Now assume that the user saves a file called termpaper.doc of size 2400 bytes. Further assume that the file system has 512 byte clusters. Doing a little math to find out how many clusters are necessary to store termpaper.doc, we see that 2400 bytes divided by 512 bytes per cluster means that it will require 4.7 clusters. But since the operating system has to allocate full clusters, we round up. So there will be 5 clusters allocated to termpaper.doc. And we see them laid out here. So here in the root directory is termpaper.doc, and the operating system, or the file system, chose cluster 0 as the first cluster. Going back, we see that all of these open entries in the FAT are unallocated space available for new files to be written. The file system could have chosen any of these clusters to write termpaper.doc. It just so happened to choose to write the first one to cluster 0. The second of the 5 clusters of termpaper.doc was in cluster 1. 1 went to 2, 2 went to 3, 3 had to go up to 5 to end it. Remember that it had to skip cluster 4 because in the previous slide we saw that cluster 4 was already allocated to test.dat. So again, we see the 5 clusters necessary for termpaper.doc are allocated in clusters 0, 1, 2, 3, and 5. As a side note, notice the slack that was introduced. By having to allocate 5 clusters when only 4.7 were necessary, some of the last cluster wasn't written by termpaper.doc. This will contain whatever was there before. In particular, it's going to contain 160 bytes of slack. Why 160? Well, 5 clusters of 512 bytes were allocated. That's 2,560 bytes. But only 2,400 bytes were necessary because that was the size of termpaper.doc. So take the amount allocated, which is up to the next cluster boundary, which was 2,560 bytes, subtract the 2,400 bytes actually used, and we come up with 160 bytes of slack, which is area on the disk containing what was there before termpaper.doc got written. And again, in forensics, that's potential evidence. Carrying on with our example, let's assume the user now deletes termpaper.doc, and let's see what happens. When the user deletes termpaper.doc, a special character is put before it in the root directory. Notice that the entry still stays there, but it's indicated as being deleted. Also, all of the clusters allocated to termpaper.doc are now marked as unallocated. Typically they would be blank like these up here, but I'll leave them as the XX just to remind us that termpaper.doc still resides there until the file system chooses to write another file over it. So again, for deleting, we've marked it with a special character in the root directory, and we've marked the clusters as free in the FAT. Now assume that the user saves a file called bills.txt. Assume that bills.txt is 600 bytes, which, with clusters being 512 bytes per cluster, requires just over 1 cluster to save. But, since we have to round up, bills.txt will require 2 clusters. So here we see that the file system chose to put bills.txt first cluster in cluster 1. Remember that termpaper.doc used to be in cluster 1, but it was marked as unallocated when termpaper.doc got deleted. So the operating system could choose to write the newly saved file bills.txt over where termpaper.doc was. In fact, it overwrote 2 of the clusters that termpaper.doc was in, because it wrote the first cluster of bills.txt to cluster 1 and the second cluster of bills.txt to cluster 2. And then here we see the end of file marker for bills.txt. So again, note that termpaper.doc, which was deleted but still there in clusters that had been unallocated, now 2 of termpaper.doc's clusters, clusters 1 and 2, are overwritten and can no longer be found. But 3 of its clusters, clusters of termpaper.doc's clusters, cluster 0, cluster 3, and cluster 5, still have the contents of termpaper.doc in them, even though termpaper.doc was deleted. This is a source of evidence in what's called unallocated space. Now, because not all of termpaper.doc is there, only part of it, and not a contiguous part, is there, a technique called data carving, which forensic examiners learn, must be used to pull out the parts of the file and try and reconstruct at least part of termpaper.doc. So that's an example of how the FAT file system manages the saving and deleting of files. Now we mentioned that the FAT file system isn't the only file system. FAT12 and FAT16 were used on floppy disks. FAT32 was used in some versions of Windows and on many USB devices these days. Modern Windows uses a file system called NTFS, which is the NT file system. It's used on Windows NT, 2000, XP, and Vista. NT is a much more sophisticated file system than FAT. Instead of using a table lookup like we saw with FAT, NTFS essentially uses database techniques to store records of where the file clusters are on the disk. And it uses database lookups and indexing techniques to make fast access to where the clusters are. Linux has several file systems that it can use. Typical Linux uses the ex2 file system. A newer one that has something called journaling is called RiserFS. All of these file systems do essentially the same thing. They tell the operating system what clusters a file has in it, and they keep metadata about the clusters. It's just how they do it. In FAT, it uses a root directory and a file allocation table. In NTFS, it uses a master file table as part of a database. ex2 and RiserFS do it differently. Each partition on a drive can have its own file system. File systems are also found on different media. For instance, CDs use a file system called ISO. We already mentioned that many USB devices use the FAT32 file system, which means they can be treated almost like a hard drive in forensic analysis. Understanding how file systems work is important for a forensic examiner because it's the file systems that are storing the data, and where they store the data and fragments of the data can help the forensic examiner find evidence that could otherwise be hidden.